So my topic today is efficient, fair, and robust multi-party computation. So the background is like we think about having multi-party multi-party computation with fairness. That's our stop point. So informally, fairness means when some party gets the results, all honest parties should get results too. However, when we look at a very efficient multi-party computation like SPDZ speeds, we found there's an issue. For speeds is an very popular example of multi-party computation. It has two phases. The phase one deal with all cryptographic tools. It generated like encrypted signal, encrypted values, and the phase two handles online computation, requests like share, add, multiply, and open. Because all the preprocessing or cryptographic steps are done in the phase one, so phase two can be very fast. So why we found why did we find the fairness? It's not a good idea to put in speeds, because when we use a Cassie approach to have the fairness in speeds, we found this goes against the philosophy of the speeds, because it's if we want the fairness, we have to encrypt the output. And so we have to put encryption in the phase two, and that will hurt the online phase two performance. There's some new approach, like released in 2022. It used NK Shamiz sharing, but this is still cost, like lower privacy threshold. That means if K parties are corrupted, the privacy will be gone, and there's no information theoretic checks in this scheme, in revenues scheme. So we think about other ways to have a fairness in speeds or speeds-like algorithm, something like some multi-party computation like speeds. That's the concept or the background of the research. So let's go to the introduction. So the speeds has two phases. The online phases is very efficient, and the offline phases deal with encryption engine and other and beaver triples for replication, and other other works which take longer time and much more complexity than online phase. Because the offline phase is input independent. It doesn't take any input data, so it can be done before the online computation happens. So that's why this phase is usually called just usually called preprocessing. Okay. And the problem happens the share opening of speeds. Um, if all honest party, if the party all parties are honest, there will not be any problem. Okay, so everyone can recover the secrets, the results. Uh, if you look at the middle, if some player is corrupted, and this one can actually steal. I say steal the results, and the other party uh, cannot do anything. Um, cannot do anything to get the results. What it, what she can do, for example, if the Alice is honest, she can find Bob is malicious. Yeah, but all she can do is to raise the warning, like abort the procedure, to abort the procedure. But even the procedure is aborted, the secrets still can be recovered by the malicious Bob. That's why we don't want to see. So the classic solutions for this problem is to encrypt, like it's just like can encrypt everything. So it requires a trusted third party to give a public key to Alice and Bob, and they encrypt. So both encrypt their own shares, and to make sure shares are corrected, they have to give the commitment, and to verify, so the other party can verify the encrypted shares. Like for example, the Alice gave the commitment, and the encrypted share is called X to Bob, and Bob does the same to Alice, and they have to use the commitment and the encrypted share, and run the Fibonacci proof to verify the Fibonacci proof given from the other party. Okay. So there are the possible outcomes if the Fibonacci proof passes. Okay, there will not be any problem. So if the procedure can just go ahead. If some parties is malicious, or cheating in the shares. You can see, for example, if Bob is malicious, so Alice just raised the alarm. It's called the Fibonacci proof verification failed. She abort the procedure, and she can put the evidence to the trusted third party, and which can blame malicious Bob. Because the procedure stops here, so either Bob or Alice can recover the secret. So no one knows the secret because the procedure is aborted. Okay, so if so there's another possibility. If the procedure is moving ahead, the zero-knowledge proof, the verification passes, and the next step is they will exchange the plain text, because of the verification for the ciphertext just passes. They have a backup, so right now they can exchange the plain text, and they will use so both of them will use the commitment to check the plain text. If the cheating happens here, the third party will give uh, the Alice, the other party will call the trusted third party to give uh, the the secret key. So the other party can decrypt the ciphertext to get the shares from the other party. Okay. So this is the classic solutions for this problem. This is called optimistic because the decryption is required only when uh, the misbehavior is detected. This concept is originally from the Oscar uh, 1997. It's originally used for signature exchange, and then this concept was borrowed to for secret sharing in caching paper in uh, in uh, in 2000. So we can say that the overhead is verify the ciphertext and the commitment using zero-knowledge proof. Yeah. And however, uh, if we use this concept to the speeds like we said previously, it's this cubesum online phase. Like so in 2021, it uses TTP to decrypt the ciphertext. But eventually it will need to decrypt all the shares for for all the outputs. So it's no longer optimistic. It means the decryption is required all the time. So we can expect the speeds and the efficiency is much lower. So our solution is to avoid a very slow online phase and still with a fairness. So that's why we use two-level sharing. The two-level sharing is like one sharing is for fairness and the other level of sharing is for computation. Because the like if the first level is to fairness and this level is input dependent, so it can be so a lot of work can be done in preprocessing phase. And for level 2 sharing, it depends on the input. So we can keep it simple and let it do its work in the the second phase, the online phase. And we still keep the original linear sharing. So these two types of sharing coexist in our scheme. So it's used like message authentication. So we can have the information theoretic checks. So there's like a cross check for two types of sharing, so that we can save some complexity, because for most of the time we don't need to do zero knowledge proof for verification. So there's two-level sharing like this. So the left side is one level sharing, is widely used in speeds MPC algorithm. And we introduced two level sharing. Well, first we have some randomly generated V and U, and we use V and U and as a multiplication factor to share the same secrets. So it's like this. Okay. So V and U is a random number. It's linearly shared by two parties, and our secret S is shared by this formula. The blue ones are kept by store, or says stored by the Alice privately, and the red ones are kept by Bob. So the blue is Alice shares, and the red is Bob's shares, and the formula is share the secret S in this formula. So that's we call a two-level sharing. Then we can prove it's a perfect secrecy if uh, if without knowing a V and U, no one can recover the secret S. If anyone want to recover S, it's first he has to recover V and U, and then you can recover S. Okay, so so the steps for input sharing is like in this way. We first let Alice and Bob randomly generated V1 U1 and V2 U2, and yeah, and both will call homomorphic encryption to encrypt their own shares. They broadcast the ciphertext, so we can have a ciphertext for the sum of the two shares. So we can have the ciphertext of V and U. Okay. And then as share randomly generated the share X prime, Bob's generated Y prime as their own share, and then the broadcast ciphertext of V multiplied by X prime. Bob broadcast ciphertext of U multiplied by Y prime. So they have the so both of them have the ciphertext of X prime. Okay. So when the input comes, the client will decrypt the ciphertext S prime, get the factor C, and the broadcast the factor C. So the S Bob can adjust their own shares depending on the factor C. So they have the share X and Y, and this formula will hold. Yeah. So the sharing is so this step is kind of special. Okay. So when opening shares, we first we reveal the level two share, because level two share is for computation. We don't need to worry about the if anyone can recover it and recover it by cheating. Yeah, because no one can recover it until level one sharing is revealed. So we can just directly reveal the level two share. Like in this formula, we can just when we opening, we first let the parties reveal X and Y, and we can use the MAC authentication, like the cross check we said we talked about, to verify X and Y. So once it passes, then the procedure will go ahead to reveal the V1, V1, V2, and U1, U2. Okay. And the procedure to reveal the V and U, the level one sharing, is very similar to the classic way. Okay. Yeah, this gives more details and goes to next one to show it. So the like the classic ones use commitment and encryption. So for to open the level one share, it use the same ways to open them. Okay. So in preprocessing steps, S and Bob will give will have the ciphertext and verify the ciphertext in the preprocessing steps, because level one shares is input dependent, so this can be done in preprocessing steps. And as Bob used this level one shares to generate some random shares and pivot tables. So unfortunately, I don't have time to talk too much about it. So if anyone interested in it, can the reader can go to read the full paper. Okay, so with this, the ciphertext of the level one sharing. So after the computation is done, the parties decide to fully open the secrets. So we go ahead to open the level two sharing. We don't need to worry about the malicious party recover the results by cheating, because no one can recover results if because it knows nothing about VNU. the BNU is encrypted here, the one sharing, so the malicious party cannot recover the results. Okay. So after the plain text of level 2 sharing is correctly opened, the party will go to open the level 1 sharing. They exchange the plain text, and the parties check the commitment. So like in the previous slides, if a commitment passes, the opening procedure will be done successfully. If it's the commit, if the verification does not pass, the honest party will call the trusted third party to give the secret key, so it can recover the one sharing the BNU, so the honest party can recover the final results. The trusted party, at the same time, trusted party will blame the malicious party. So let's talk about the overhead to have the two-level sharing. The overhead is mainly coming from the level 1 of the sharing, because it needs to encrypt and commit the shares. It needs the non-interactive zero-knowledge proof, and they need to exchange the ciphertext, zero-knowledge proofs, and commitments, and it should be verified in the offline phase. It's the overhead in offline phase. The overhead in online phase is smaller because we don't need to encrypt the sharing level 2 sharing in online phase. The overhead we need is to verify the commitment of level 1 sharing. That's the only overhead in online phase. For misbehavior, we check the level 2 sharing by the commitment, and we also might need to decrypt the level 1 sharing. So that's so this decryption is the overhead if the cheating happens. So this is a comparison to this work to other works. So one can see so one can see our works. We still need to decrypt the shares to open, but it's optimistic. That means if all parties are honest, we don't need to do that. For revenues work, there's no decryption to open the shares. That's the advantage of this work, but because it uses Xiaomi's share, so we have to notice the privacy. Its privacy is limited because there's only K corrupted player can break the privacy. Yeah, that's a difference. And how to verify it? Revenues work don't use don't use information theoretic check. You use a commitment and check the zero-knowledge proof, which is which incurs a large overhead. Our work uses information theoretic work, and we theoretic check. Information theoretic check occupies the network bandwidth with lower computation complexity. So that's another difference for our work. And the other point we have to notice about our work is our work verifies the result first before fully opening it. And for other works, it reveals the results and then verify. Yeah. So that means the opening procedure is will have a fairness issue. Yeah. So that's why. So the revenues in revenues 2022 work, the fairness issue should be solved by the Xiaomi's sharing. It cannot be fixed by the opening procedure because it reveals results before verification. So that's about the fairness and more comparisons. As for the robustness and the zero-knowledge proof generation. Our work generates zero-knowledge proof only in online phase. For other work, in only in offline phase. Sorry. For other work, the online phase. In other works, the online phase also needs zero-knowledge to check zero-knowledge proof, which takes much longer. And for robust, Wang's work has a limited ability to support robustness, and our work is yes, even if there's only one honest player. Okay. So that's a conclude of my work. So we designed a space like MPC with optimistic efficiency. We use 2-level shares. Our opening is fair and optimistic, and we use verified encryption in the preprocessing phase. And for online phase, it is no decryption and authenticated for level 2 shares. And if there are all honest party, we don't do any decryption. And our robustness is supported by the fairness and identifiable abort, and we don't have time to cover it. So the full paper discusses about this one. So our future work includes more efficient online phase, because right now our online phase still needs to do a commitment check and decryption if someone is malicious. And also we need essential more simulation data in different scenarios. That's our future work. So thank you very much. This is my talk. Thank you for your attention.